Well, welcome back to another edition of our Liftoff webinar series. My name is Joe Steele. I'm the Senior Director of Communications and Legislative Affairs here with LIFT. Thank you very much for taking time to join us today. And we're excited to have this webinar today with two of our member companies talking about a project that they worked on together, which is really innovative. And we are excited about it at LIFT, and hopefully they are just as excited as we are. And hopefully by the end of this webinar, you will all be as excited as we all are about this this project. So we have a couple of Daves joining us and a Scott. So a couple of Daves and Scott talking to us from Bond Technologies and from Boeing to talk about some refill friction stir welding of aerostructures, a project that they just concluded and got some interesting results on. A couple of housekeeping items before we get started. Everyone should be on mute. If you are not, please go ahead and do so. We are recording this session and we will post it on our website at lift.technology. You'll be able to find it there in case you want to revisit something or share it with folks who are unable to join for one reason or another, or folks that you just think might be interested in the topic. So please go ahead and do that. We will also host a Q&A session after the presentation. So please use the Q&A function, avoid the chat function, use the Q&A function. That's a little bit easier for us on the Q&A side of things. You will do that at the end, but throughout the presentation, you can go ahead and chime in with any questions you might happen to have. So with that, I want to share a little bit of information about LIFT. For those who may not know who we are, what we do, we are a nonprofit, public-private partnership, Department of Defense, National Manufacturing Innovation Institute. That is a mouthful, but really what we are aiming to do is drive American manufacturing into the future through technology and talent development. We know that our national economy, our economic resiliency rests on advanced manufacturing, and we want to make sure that the U.S. is the leader in that to maintain, regain our manufacturing superiority. So that is our mission in life as a nonprofit public-private partnership. We are working with our partners like Bond, like Boeing, to accelerate technologies to get them into the hands of the warfighter and into the hands of the commercial sector as quickly as possible. So how do we do that? So at LIFT, we are solving the manufacturing equation. We really work at the intersection of material science, manufacturing process, systems engineering, and the talent really that runs underneath all of those. Basically, we're trying to figure out, okay, we know what we need to make in the future. What do we need to make it out of? How do we need to make it? And to make sure that it is fit for purpose in whatever system it is going towards at the end of the day. You also want to make sure that the talent to work with these innovations that are coming out of our partners like Bond and Boeing coming out of LIFT, that the talent exists to work with those new innovations as quickly as possible. So you're going to see and hear today a little bit about some manufacturing process that this project revolved around. So really, we have run two programs at LIFT: the Leading Innovations for Tomorrow, which is our technology program, and Learning Innovations for Tomorrow, which is our talent program. A little bit about the Leading Innovations for Tomorrow technology program. As you see on the screen here, those are our 4 pillars of technology. All of our projects and programs fall under one of those pillars in some way, shape, or form. But as you can tell, it really is materials research, manufacturing process, and systems engineering. We're really trying to get that loop so we can design, build, and test, so we can make things better, faster, cheaper for the industrial base and for the warfighter. You can see on your screen, starting with ICME, really the virtual side of things. Can we virtually model and simulate materials and processes so we can better understand what is going to happen to a material during a process, so we don't have to make it and break it. We can do things a lot faster, so the whole system is better, faster, cheaper. Moving to the right, advanced alloy and process development. We're talking about things like lightweight armor development, rare earth materials, hypersonics materials development. Can we develop these new materials that we'll need for things in the future? And then as we develop these new materials, you see the multi-material joining. How do we join these things together so they're fit for purpose at the end of the day in whatever system they need to enter into? And then finally, bottom left, agile and smarter manufacturing. Can we take a look at more nimble manufacturing processes, things like wire arc additive, cold spray? We've got incremental sheet forming in there as well. All of these technologies and processes are being worked each day at our Detroit facility, again, trying to accelerate these technologies into the future. A little bit about our talent program. Again, this is still about innovation, still about new ways of doing things, but this is now we're looking at new learning tools, new pathways, new venues. That really revolves around our Detroit Lift Learning Lab. That is where we really take a look at new curriculum, new ways of doing things, test things out here, and then roll our programs out around the country. We've developed a Ignite Mastering Manufacturing curriculum that is a curriculum for high school students, a 3-year program for high school students where they are exposed to advanced manufacturing, seeing what it looks like in 2022, putting them on the path to being that multi-skilled technician that is so needed in the manufacturing base. That program, which started here in Detroit, is now available to about 3,500 students around the country in about 13 states. So we are rolling that program out to, again, try to make sure that that advanced manufacturing pipeline is healthy and robust moving forward. And then for our more adult learners, our more mature learners, we offer some certification courses, nationally portable, industry recognized credentialing programs in CNC, machining, welding, industrial technology, maintenance, and robotics. We do that here at our Detroit facility as well. But we also have a program called Operation Next, which is geared towards our service members. As a Department of Defense Manufacturing Innovation Institute, we want to make sure we're providing opportunities for our service members to begin their civilian careers, their next mission. So we offer them opportunities to earn those certifications as well. Both active duty folks as they're beginning to transition out 6 months before their separation date, as well as Guard and Reserve members and their families, spouses included. Sometimes those folks are unemployed, underemployed. So we want to make sure that we're taking care of those military families as well. So that's available in about 13 locations around the country, mostly around some of our bases that are available or that are around the nation, and looking to expand that going forward. So a couple of things that we are trying to do. I mentioned that we are a nonprofit public-private partnership and also a membership-based organization. So I'd be remiss if I didn't suggest what we offer our members. So you see those on the screen here. The Lift Advantage, we're a trusted advisor. We're not really selling a product or service. We're just trying to put the best teams together and give our own expertise along with the expertise of our ecosystem together to move the needle in advanced manufacturing here. Technology Accelerator, I mentioned trying to move these technologies forward. We are not an incubator. You're not going to find a lot of startups and things like that just getting to work in our Detroit facility, but we are taking things across that manufacturing valley of death. If you're familiar with MRL levels, we're operating in that 4 to 7 space, trying to move these technologies forward. Technology Showcase, Showcase and Sandbox. Really, if you haven't been to our Detroit facility, I encourage you to do so. Not only are we showcasing the future of advanced manufacturing, but really working it each and every day with our technology team, with our partner members. Connector and a convener, thanks for joining us today. That's why we are here, to bring the best and brightest minds together. Talent developer, we already touched on that, but again, making sure the advanced manufacturing pipeline is healthy and robust moving forward. And finally, a government partner. It can be intimidating or overwhelming for folks to begin working with the federal government. Dave H, I shouldn't say Dave H, there's 2 Dave H's with us today, but Dave Hofferbert from Bond, he might be able to comment on that. But we like to serve as that conduit for folks to begin working with the federal government. So that is Lift in a nutshell. Any questions, please, reach out to us, visit us on the website, send us an email, give us a call, follow us on our social channels. We'd be happy to entertain those questions, or if you'd like to become a member, please go ahead and do so. So that is enough for me. I'm going to hand things off to Dave Heck from Boeing, as he's going to lead us through the presentation on the project that that Bond and Boeing worked on together. So Dave, if you want to go ahead and share your screen, we will hand the presentation over to you.
Okay, everybody see that? I hope.
Yeah, we got you.
Okay, a few introductions first and background. I'm David Heck. I'm the Boeing's lift representative. Scott Rose is our lead welding engineer, and also on the team, but not on the slide, is Dave Hoferbert and a couple of his people from Bond. I'll say a little bit about where Scott and I are, and then give Dave a chance to talk about Bond. So Scott and I are both in St. Louis. We're former McDonnell Douglas people who were merged with Boeing back in '96. We're part of Boeing Research and Technology's materials and manufacturing technology team. We do all sorts of things. We've been doing additives since '96, additive of titanium. We've been doing friction stir welding for longer than Scott was here. And specifically for the refill friction stir spot welding, we've been chasing that for many years. Scott has been doing that. Have made some big strides, but really haven't delved into any of the military applications, and that's kind of where we are going with this whole project. Dave, you want to say something about Bond?
Sure. I'm Dave Hoferbert. My title is president of Bond. We're a small and I would like to think nimble company in Elkhart, Indiana. We've been involved in friction stir welding for many, many years, since the early 2000s, and mainly as an equipment provider. So we've become knowledgeable about the solid state joining processes such as friction stir welding. We branched out into refill friction stir spot welding relatively recently as an equipment provider. And we also are dipping our toe into additive friction stir deposition as well. So we do a variety of solid state processing, but we are mainly an equipment provider.
Okay, so on we go. If we can go on. This is just basically a breakdown of the project final report. I've taken out all the programmatics, as that really hasn't any real application. So talk a little bit about the objectives when we get to the actual spot welding work and development data. We're gonna switch to Scott and then back to me for the rest. So as you may know, friction stir spot welding has been around for a while. There are some issues with it, but the goal is to replace hand riveted holes, which are used throughout aerospace, certainly on aircraft that are mostly metallic. We've been spending a lot of our time on commercial airplane applications. So, and again, there's even with 787, there's still places that there's aluminum to aluminum connections. So those are all possibilities, depending on the size of the actual hole and the loads in the structure, et cetera, et cetera. We're focused on refill. I think I have a slide. Nope. We'll see that in a couple slides because it produces a better joint. It actually takes the material that it pushes out of the way and stirs in, and then pushes that original material back into the hole. So you get a very smooth surface on the anvil side, and then also on the inside. So there's no divots or anything like that. And as the last statement says, we've reached TRL 6 for our own internal work. Let's see. So our project was, we want to look at other applications that are more military focused. Again, there's lots of places on lots of airplanes, F-15, all the helicopter programs, and some of the military derivatives like the P-8, which is a 737 derivative, and KC-46, which is 767. So what we wanted to do was find a target component that we could actually transition this technology to. So in the ranking of parts that you use as candidates. You usually start with doors and removable things for your first entry level transition. That way, if something goes wrong with the process, even though you've vetted it and done all the testing, if something goes wrong, they can just take it off and put a new one on. And then you go into secondary structure, and then into primary structure, and then into you get that high into higher criticality level stuff. We don't really think uh, friction stir spot welding will be in anything in the critical section, because those are usually titanium or stainless steel or other fasteners. So we did development of weld parameters. We really wanted to check how fast we could go from weld number 1 to weld number 2, 3, 4, 5, and 6. We'd seen some data from other partners that have worked with us, which were including Bond. Bond's worked with us for a while, just to see how fast we are. And again, some of the previous stuff we saw was maybe 6 seconds per weld, which is we can drill holes with an automatic machine pretty close to that speed, but we certainly cannot go back and rivet those holes, even if it's automated, in that total amount of speed. So right off the bat, it looks like it's at least equal. And again, you get some of the labor hours out of it. And, you know, application of our multiple automated drilling methods that we have, you know, a dozen different ways to drill holes. So we wanted to see what the strength is, what the finish looks like. And again, the real time was the thing that's going to be the real winner. So in addition to that, we did a cost model at the end, because we really wanted to see, you know, is this really going to be cheaper? The machines you use going to have to be really, really expensive, and therefore you're paying them off for every assembly as you go, and it takes a while to pay it off. Or is it going to be sticking on the end of whatever robot you have, and off you go? So this is originally part of a large proposal that we wanted to actually go and physically make this Apache component and demonstrate that, yeah, we can do all of this stuff and then deliver it to the supplier that actually does the rest of the assembly. So again, that's hopefully still to come. Just for your information, we've got a new version of the Apache. It's the AH64E version 6 that has some engine changes and performance increase, range, whatever, reliability, better displays, and all that stuff. So there's still a possibility we can start worming our way into production. So this is the refill spot welding method. So you basically have a clamp on either side of the hole, cylindrical. You push the shoulder down into it while it's rotating. Rotating the pin, that the shoulder pushes the material up into the pin void, and then the pin pushes it back down to make a nice smooth surface on the inside. And again, being up against an anvil, a smooth surface on the outside. And this is Bond's machine, and a diagram of what the actual friction stir refill friction stir spot weld device looks like. See how far we go into here. So again, we talked about the Apaches. Part we looked at is the engine and cell door. So the engine is actually sitting in here, and there's an engine on each side. This door folds down along this hinge line, and this actually becomes a work stand. But it's got obviously rivets all over the place. It's got some pin and collar, like nuts and bolts kind of fasteners too. But the ones we chose were obviously the ones that are just regular rivets. Looked at other applications, again, looking at low criticality parts. So doors that come on and off, metal flaps, etc. There's also some teams looking at in-service repairs of aluminum skins on fighter jets and whatnot, that you can go in and just push a new piece in and not only do the weld, but also fill any cracks or anything like that. So, but that wasn't part of this. So again, I kind of talked about this a little bit. This part's double contoured. So when we do it, it's going to need to be robotic. A little bit of a challenge, but we're pretty sure we can do it. We've done all kinds of things with robotics. The outer skin assembly, which is you're looking at the actual inner skin, but once the door is closed, just the outer skin has 516 rivets, which really isn't very much. There's hundreds of thousands on commercial airplanes, so the more rivets you can get to, the better. So if we show a positive business case with this, then other portions of the structure of the helicopter are open up as possibilities, as do other aluminum helicopters like the Chinook. So I'm going to pass this over to Scott because this rapidly gets out of my wheelhouse with this. So Scott, go ahead.
No problem. So yeah, as we're doing this program, it's kind of, a smaller, shorter program. So we wanted to quickly get a bunch of details out of it. So we used a design of experiments to really throw a bunch of parameters out there and try to figure out what the best options were. Now, rather than just doing a single spot, we made it on a 10-spot coupon, so we can get to see, how these plates manage as we're going down the length. So we used 4 variables. We either skipped 1 spot or 2 spots to let that heat dissipate as we were welding. And then we used the RPM to adjust the heat input. We looked at different plunge depths to see how far down we're going into the lower sheet. So that can affect both your lap strength, but also, again, how much heat you're putting into the surface. And then a tamp depth, which is, after the initial weld, you push down a little bit just to make sure everything is solidified and gives you get a nice clean surface at the end. And looking at our output variables, looking at the surface roughness, because this does have to go through the air and have a nice smooth surface on the outside. The lap shear, as we're comparing to a rivet, which is same for the fatigue. And then also doing a metallographic cut just to make sure you're getting a good consistent structure throughout the spot weld.
So a few more things I want to point out here that were on slides earlier, but didn't make it into this set. But, a lot of with any friction welding process, your primary variables are what your materials types are, what the heat treats are, and what the thicknesses are. With each of those changes, you have to come up with a different set of parameters that'll give you the best set of properties, and you have to lock that in. In this case, we were looking at, again, 7075 and 2024, but they were both, one was 020 and the other one was 030 inches.
That's on the next slide, Dave.
See, I'm jumping the gun. One other thing that Scott mentioned was with the smooth outer surface. That's really not a requirement for the Apache. They have protruding head rivets just about everywhere, but I'm sure if you replaced all of them with flush surfaces, that would obviously help the airplane move through the air faster or easier. Okay, there you go. Oh, look at that.
So as Dave was mentioning, these are 7075 and 2024, but very thin. You have 50 thousandths thick is for the total thickness where you're putting the weld or the rivet. So these were done with a 9mm or 0.354 inch diameter tools that were spaced 1.2 inches apart, and with an edge distance of 0.6. We're trying to keep a lot of the same parameters when you're doing a rivet replacement. So keeping an edge distance, looking at your overlap and your spot spacing. So these all equate to at least 2D and 2D for edge and sheet overlap, as well as a 4D spot spacing. Again, for a 032 to 020, so pretty thin material. So it can be susceptible to a lot of the other properties that we're messing with. So just to showcase, as we're stepping down to do the lap shear and the fatigue. Go ahead, Dave.
And those sizes that Scott mentioned, the edge distance being 2 times the diameter and the rivet spacing being 4 times the diameter. That's typical values for aerospace assemblies. Twice the diameter. Edge distance of twice the diameter gives you the best fastener bearing stress allowables. Really is not the case here because there's actually not a hole. You're not pushing hole to hole, you're pushing solid material to solid material. So it's actually a better joint. But again, there's standards that everybody wants to see, and we thought we'd start with the aircraft standards. So next slide.
Yep. So, as mentioned a couple of panels back, we did have to do a 3 repeat panels. So we were doing these in rapid succession, one after another. We did get some buildup on the tools, which caused the touch point to be off. This is, doing research and trying to push it into full scale production really fast. You see some things like this, but we were able to, go through a procedure and make sure you can, just see what the tools look like, both cleaned and before they got cleaned. But we could do this in process as well. So those final 3 panels were able to be run without any issues, just running some additional cleaning trials on the tool itself in process. So we were able to, starting with the surface results, surface roughness, what we did is we measured the bottom sheet, so the bottom of the bottom sheet, which would be equivalent to the side that sees the air flowing past it. And we measured the surface roughness both in the length of the weld and across. So we do essentially a plus sign on the back of the weld. And all of them were within 125 microinches, which is a typical requirement. And most of them were under 63 microinches. And even under 32 microinches. So pretty much as flat as you would have a normal sheet that would be delivered to you, is sitting around at 32 microinch surface finish. And then running through the statistics, we didn't have enough panels to get interactions, but none of the variables we looked at really drove one way or the other for some of these surface roughness. So, if anything, we just saw that there was no buildup. So as we went, panel to panel, we didn't get heat buildup to cause extra surface roughness. So it was more good to see that it was not affected, but we could still get surface roughness that met what the blueprint requirements were. And then for lap shear, we were able to do the first set of panels. We were able to get all those pulled for for the lap shear strength. The repeat panels were unable to be pulled before the end of the program, so we weren't able to do a full statistical analysis. But even looking at what we did get, we did get at least 2.7 times stronger than the blueprint riveted joint. So this is comparing to a MS 2470 AD rivet. So that's the aluminum rivets that are currently on these panels. They carry 150 loads in shear, 150 pounds of load in shear. And we were able, across the 5 panels we were able to test, we had 405 pounds of shear strength. And if we throw out a couple of those panels that didn't perform as well, we were able to increase that average up to 505 pounds per weld. So quite a bit of a jump in the shear strength of these. And these are material to material, no rivet head there to help you, no actual rivet there. So we were able to get some pretty good strength out of this process. But we weren't able to get the fatigue or the lap shear testing completed for the statistical analysis. So another thing we did, we wanted to talk about speeds. How fast can we go? So one thing we were trying to do is, how fast can the individual spot welds go? Bond's process engineer worked on that and tried to increase the speed. So he was jumping up the individual feed rates of different parts of the spot weld up 10%, 25%, all the way up to 100%. So full 200% speed of what he was commanding the machine to do. And so all of these travel speeds here, 420 millimeters or 240 millimeters per minute were the feed rates for the individual plunge sections of the weld. I didn't really see any differences in the forces that were being exerted on the tool or the surface finish on the backside. If we go to the next slide, Bond did a pretty good analysis of looking at what's happening on the right. So we have the different shoulder loads, and the pin loads are the orange and gray, with the blue being the shoulder speeds. So you can see where the tool is starting to spin up in the blue, and when you start to push down on the tool. And what he saw, so the original DOE welds were about 1.2 seconds long to do start to finish. Once you start plunging until you're pulled out of the part, was 1.2 seconds on those first DOE welds. And when he increased to a 200% speed, he got that down to a whopping 0.98 seconds. So we did get a 20% increase in speed, but again, it was still, about a second long, which was much better than the 6 seconds or so that we had stated earlier. And so a lot of what your time is going to be is going from spot to spot. So positioning the robot and putting it in the next spot is going to be more of your time than in the actual spot weld itself.
Okay, so back to me. One other thing about that discussion with, or the statement Scott made about the robot speed. Typically, these holes aren't very far apart. So if you look at the 4 times the diameter spacing, if the hole is 0.35, well, 4 times that is 1.4 inches. So the robot doesn't have to move very far. So we don't expect that to be more than 2 seconds. So looking at that rate, clearly have drastically reduced the time it takes to rivet. We do it much faster than it takes to drill a hole. So it's, I think it's got a lot of potential for further work and applications all over the place. So anyway, I made a cost model for this. Part of my time, in addition to being a metallic processes application engineer, I've been spending time helping a team we have called the Teardown Lab, which does the same kind of thing that automotive companies do. We buy products from those other guys, and also our own products, and we take them apart, look at them, see how they're designed, how they're fabricated, and then do cost estimations to see where their cost really is and compare it to ours and see, if theirs is cheaper, why is it cheaper? If ours is cheaper, why is ours cheaper? And what the design benefits are. So anyway, so looking at the whole assembled door, we took out anything that was the same. So anything that wasn't a riveted assembly that we're going to replace. If it was traditional fasteners, we didn't look at those. We're only looking at the delta between the riveted and the spot welded. So what we looked at was time to locate the skins and tack rivet the stiffeners on, and it's some of the stiffeners, and then how long it takes to drill with tooling and inspecting, and then you got to disassemble it, deburr the holes, and reassemble it. Then it's a 2-person riveting operation, and then there's going to be non-conformances and rivets that aren't circular, and the heads that are rolled over sideways, and that kind of stuff. So for the stir welded version, we looked at locating the skins and stiffeners. Again, doing a little bit limited amount of riveting just to get parts in position and to hold them together. And then the operation we looked at was 2 seconds a hole with 1 second reposition time. And all this included the cost of the machine, especially the discount rate that Bond's going to give us when we buy these from them. But the cost of robots, electricity, maintenance, everything that goes into the true cost of that device. So it's the method we use during our teardown cost modeling is very much from the bottom up. We look at washers, rivets, everything you do to make that part, including inspection and NDT and that sort of thing. So for the riveted version, we had an internal tool, this one, that lets us estimate how much it takes to load particular parts in the fixtures, how much it takes to drill, deburr and everything else, and then install the fasteners. So for this case, the assembly cost for those 516 holes was $2,170, which isn't a big number. If you're making 200 of these, it becomes a little bit bigger number, but for this limited part, it's kind of what we expected. we put this, roll all this information up into, excuse me, another program called Clean Sheet, which is by McKinsey. That lets us look at specific operations, break them down piece by piece. So again, you can look at if it was a part you're going to machine, there's a certain amount of material, certain number of cutters that are a certain cost, and then a certain amount of setup time, and then run time, and et cetera. Then go into the inspection part of penetrant inspect and sealants and priming and everything else that goes on to make a part. So we can specify where the machines are, what machines they are, custom machines we can customize, all kinds of stuff. So we get a really good output from this that we can change if we need to, like logistics and profit and all those other percentage. So it's a really pretty good tool. So again, we looked at a weld rate of a little bit faster than I said before, of 1.5 seconds, or a little bit slower. Sorry, 1.5 seconds per weld plus a reposition time. For the robot, we used a higher end automated drilling robot, and this is the specs on the robot. So total cost is $2 million. That's really crazy high, but still, it's this is what the software gave us, and we could go in. We didn't have time to go in and modify that to get quotes and that sort of thing. But the next system in the database below this one was well below what we needed. Didn't have the lifting capability, and certainly couldn't put in the right amount of forging force. So when we broke it all down, and this is the way we show this. Basically, everything on this side of this chart is built up to the direct manufacturing cost, what it actually costs to do that work in whatever facility you're doing it, before you start adding on all of those overheads and that nasty profit thing. But it gives you an idea of where's the money coming from. You're actually spending less money on labor and more money paying off this $2 million machine. If that machine was a quarter the price, then this was come down also, because it's the amount of time you're actually operating that machine. Anyway, the bottom line came up with a total of just over $300, which is, considering you're moving 2.5 seconds a hole, that's pretty good. That's a pretty good rate. So we look at it, the total cost of adding the welding tools and to it. We came up with a total savings per aircraft. So it's one door on the left, one door on the right, of $3,700. And for 200 aircraft, that's, $750,000. That's not too bad. Non-recurrent cost. Yeah, we got to put robotic equipment in. The outrageous cost that Dave Hofer is going to charge us for that friction stir welding head, and then time to actually program the machine to go off and do it. So total program savings we estimated was $650,000, which is a pretty good number for just 516 rivets. If you can look online, you can see illustrated views of the Apache, which is the one where I had the pictures of the door. But you can see all the rivets in the tail, especially in other places. So there's thousands of rivets. So this number could get to be, $3 million per ship. Well, that's a big number. That's a good savings. Now, granted, we make our profit based on a certain percentage of the sales price, and there's a federal limit to how much we can make. But most of our helicopters go to foreign sales. So if we can cut the price by a couple $1 million, well, that's going to mean we're going to sell a lot more. So, that's the reason why we do cost reductions, because our profit would actually decrease a little bit. So let's see what else I have here. So a few more comments on the model. Rivets are pretty cheap. You look at, they're a few dollars a pound, and there's a lot of rivets in a pound. But again, as we get into talked about, there's in the tail boom skins, there's over 3,000 rivets. So we're usually looking at 2 million savings for that. And then there's other places around that, again, aren't that highly loaded, like the skins around the cockpit area. Anything where you get near the engine, then things get, sky high static loads. And the other thing we didn't really mention is the whole fatigue environment of a helicopter. In addition to the flight loads, which is really where you usually determine your fatigue spectrum, there's also that constant thumping in the background of the rotors going around and the tail rotors spinning, which drives that fatigue stress even higher. So that's something we really need to look at is how it's going to behave in a combination of low cycle vibration plus varying flight loads. And then we also need to do a larger sample of the weld speed test just to see how fast we can really go. I mean, you do 10 welds in so many seconds, that's great. Well, now you got to do it not really on a flat pan, but you got to do it with 5-axis motion with a robot with an offset, and you got to move from here to the other stringer or whatever, and the numbers might go down, but I still think it's going to be a really high cost savings. So the follow-on program I talked about earlier, we want to move this up to where we can actually put it in production on a military unit. So the proposal we had put forth was to actually make a full-size set of skins on a real metal tool that would provide us the reaction for the forging forces, and would use actual parts that we'd purchase from our supplier. I think at one time we were buying these parts from Poland. I don't remember where we are now, but again, to go and fabricate a full-scale demonstrator and do more tests and everything. So we were thinking it'd be like $1 million program. Given that we're doing a new Apache model, that might be something we can squeeze in, maybe twist the Army's arm, get Lift to help us twist their arm. Hint, hint, Joe. So again, what we showed was that we can weld very thin materials without, I don't think we talked about the warpage at all. I think we left that part out, but the big concern was as you spin this tool and push into the materials, the concern was that the material is going to buckle and wrinkle and from the torsion. We didn't see that at all, which is good. Says that the strike numbers are really good, and again, we can achieve a pretty significant cost reduction just for this part, these two parts. If we go to more parts, then we get more savings and could start looking at a pretty significant cost savings. The other thing I'll say just briefly, I know the automotive industry has been looking at this. I don't know how much work they've done here, but 2 seconds a weld is, I don't know what the typical weld cycle is for door assemblies, or I almost said fuselage, but body assemblies. But this sure makes a big competitor that you can go in and just pop it in. You don't have to bring a whole bunch of electricity. You don't have spatter and the big heat affected zone and everything else that you'd find with a normal weld. So I think it's got a lot of possibilities, and we certainly are going to be taking it further internally. So, Joe, you want to go back to the questions section?
I will unmute myself. There we go. Thanks for that. Thanks for the presentation. As I mentioned, this was a really interesting project for us to be involved in, and for us to see what you guys had cooking. And you answered one of my questions, which was other industries that this might be able to enter into, whether automotive or other other places where rivets are needed, might not be needed anymore with this new process. Could potentially be, I mean, you're still testing it out. Certainly you want to take it further, but do you see a possibility for high speed, high volume opportunities for a process like this?
Yeah, I think if we can, well, I'll let Dave Hoferbert talk to that because he's the guy that did the actual tests about speed and large number of holes and can you maintain a good rate, et
Yeah,
cetera.
the cycle time is actually on par with resistant spot welding and self-piercing rivets if you go through the full cycle time from joint to joint. Not quite as fast as resistant spot welding, but certainly well within the ballpark to be of interest to the automotive folks. The other thing is that the benefits over rivets, particularly self-piercing rivets like you see in automotive or aluminum body structures, is that you can use the same tool set for various material thicknesses and just change the process parameters to be able to accommodate different thicknesses, whereas SPRs or self-piercing rivets
Mhm.
require a different item number depending upon what the thickness is. So
And you don't need the bins of millions of rivets sitting off to the side to fill your process.
right.
There's millions of rivets that I would knock the box over and spill all over the floor. The other thing to mention is, the detrimental effect of both the resistant spot welding and the self-piercing. Self-piercing tears up the material pretty bad. I know that there's most cases they're not looking at the same kind of, they don't have anywhere near the fatigue criteria that a helicopter has, but still you're ripping into bare material and there's going to be corrosion issues and again, you're not making all those bazillions of rivets, and there's a green savings there too that we really haven't investigated.
Yeah.
So I think there's a lot more to do, and it's got a lot of promise in a lot of different ways.
Well, I'm glad in my introduction I said better, faster, cheaper, because I think this lends itself to that. I think you touched on that in a couple of different ways, and folks see that this will fit right here in our wheelhouse of materials research and really manufacturing process is kind of where this sits. How can we manufacture things in a way that enables that better, faster, cheaper results. So if you do have a question, please use the Q&A function. We've got a couple of questions here. I'll try to get in as many as we can in the time we have remaining. I do want to be cognizant of folks' time, so if we can go through these, I'll do my best. I think I saw someone raise their hand, but just go ahead and put your question in the Q&A function here. So question comes in about the measurements discussion that was had early on. Were those done via a scope or a profilometer?
Those were done with a laser profilometer. So I took it to my NDE group here in St. Louis and had them do the testing on it.
There we go. Excellent. Do these rivet or not these welds comply with either the shear pin ASTM B768 or the pin bearing E238, both of which are require qualification testing or tests?
So I have looked quite a bit at how to do these for MMPDS. We've typically just done the lap shear testing. We have not really. We've done some cross tension testing as well. We've not done the pin bearing and the other. We're more using the lap shear and cross tension from spot weld standards as they are currently.
All right. More to come as Dave Heck mentioned of follow-on project trying to explore it even further. And if you need some arm twisting, Dave, I think Lift will raise their hand to help twist some arms to enable this project to move forward. I think our CEO is on the line as well. I'm sure he'd be happy to twist some arms.
Well, I'm glad this is being recorded.
Exactly. Do you see the opportunity to create a multi device that perhaps does two staggered welds at the same time?
That's kind of an equipment question, I guess. So
Yeah.
I'll field that one. The complexity of doing ganged welds may not be offset by the benefit, but that's something that's worth exploring. Right now, we've built a single probe head design, and that's what we're running with so far. Perhaps when the TRL and the MRL levels get closer into the 8 or 9 range, you can look at different configurations that can speed up throughput like that.
Yeah.
The other thing
That'd be interesting.
regarding big aircraft assembly like commercial airplanes, the barrel sections of each of the 6 or 7 different sections are hundreds of inches long. So we have flexible drilling systems that can hit every other frame. So every foot there's another robot drilling holes. So we could see multiple robots acting simultaneously inside the fuselage. So same thing as you would have multiple riveters manually doing it. We could have multiple robots and really cut the total cycle time down.
Yeah. I did mention our CEO Nigel was on the
Yep.
line, and Nigel, if you want to go ahead and unmute, you should be able to comment.
Yeah, super. Can you hear me, Joe?
Yep.
Yeah, so gentlemen, this is awesome work. We're so happy that you've done this work. I heard the comments very clearly. I can't speak openly, unfortunately, about some activity that some of you know will probably happen in a couple of weeks' time that could take this rapidly forward with some decent funding. I've been following this work, and I really do think that it's a win-win-win. I mean, it's a win for Boeing, it's a win for Bond, and it's a win for the Manufacturing Innovation Institute program if we can keep this moving along at best speed and move it into the commercialization phase, as stated by the 3 of you. Whilst I've been listening, I've actually sent an email to Noel Mack. I don't know whether he's online here. I do know that he's in Washington, DC at the moment.
Yeah.
Asking him to convene an internal lift meeting so we can work out on our side what we actually think we can do to keep the ball moving down the field, because this really seems to me like it has very major implications, not only for the Department of Defense, but also for the general commercial sector. And I'm also, as an engineer, incredibly interested to see, what effectively is a mechanical joint that's being produced. And I heard the comments about self-piercing rivets. As a young man, I was putting self-piercing rivets into the Audi A8 automobile, that all aluminum thing back in the 80s, and I can actually remember running into the chief engineer and saying, I've got it. He said, go away and test it in a crash rig, and I did. And of course, the first rivet failed and it zippered down the structure and the whole ththing fell apart. So yeah, this is awesome work. So grateful to have both Boeing as a very, very large, credible organization deep into this, with Bond, which is a very small but innovative and indeed credible organization, leaning into this for the benefit of the nation. Thank you, gentlemen. Thank you.
Thank you for the kind words, Nigel.
Thank you, Nigel.
Thank you.
Yeah, mentioned his name and that he would twist some arms, and sure enough, he's wants to move this project forward.
And just an FYI for you, Nigel, we've done work with Ford and a few other companies, one of which was doing incremental sheet forming back when Alan Taub was CEO. So we're easily work outside the industry in another area, industrial sector, just to move it forward. So
yeah, Dave, I've absolutely got that. If you could just indulge us for a few weeks so that we can have our internal meeting. I think Noel Mack pretty well, with his automotive background, and of course we've got Hadrian Rory and Alan Taub sitting around in the background that we can access. I think we need to just have an internal discussion, a lift discussion about how big, how quickly we feel we can push this. Then what we'll do is we'll come back to you colleagues, get you involved in that dialogue to speed us up or slow us down from whatever we think. I'm feeling pretty good about being able to get significant funding behind this to actually carry it directly into the commercialization phase. Yeah.
So we did send a proposal to Hadrian years ago about the bigger program that this came out of. And Scott has more information about other work we've done with other suppliers. So we'll definitely give you what you need to help show that this is a lot further along than just a couple guys at Bond and one guy at Boeing just squishing metal and hoping it works.
I think this is a technology where the path to raising the TRL and the MRL levels are fairly well defined. So it's a matter of funding, turning the crank, doing some solid engineering, gathering and analyzing the data, and then organizing it. And I think you'll be surprised at how quickly we can move this into a viable, reliable production process.
Yeah, and I probably should stop talking after this because we've run out of time. You know, as an engineer myself, I get the point that a huge amount of de-risking has already happened here, and I can see myself, you know, a path forward, and I'm not the expert in this, so I'm sure that you know, you guys can actually look at this and go, hey, this is pretty risk-free at this stage, and we just need to go through the normal engineering processes so that we can verify and validate what we have here, create use cases, and away you go into commercialization.
Yep, and thank you for that. So we are running up rapidly out of time, so I think we may have to send some of these questions to directly to both Daves and Scott to answer offline. So there's some questions about corrosion, some ultimate material discussion, and some other you know, engineering and manufacturing process related questions. So if we didn't get to your question, no worries, we will get them in front of the Daves, and they can answer offline. So hey, hopefully folks, you know, seeing through the presentation and from the previous discussion with Nigel and team, that I mean, this is one of the reasons we exist, right, is to help accelerate these technologies, provide the opportunity for these technologies to be accelerated, and to connect, help companies big and small work together on an innovative project like this. So that's again, all those reasons is why we are very excited about this this particular project and the outcomes that you've seen so far, and hopefully we can continue to push it forward. So with that, we will have to close down the questions, but as I mentioned, we'll get them in front of the team so they can answer offline. But Dave and Scott, certainly appreciate the presentation today. Appreciate your membership and working with Lift, and hopefully everyone enjoyed the presentation, and we will post this onto our website in the near future here, so you can revisit it and get you guys connected to the folks who can best answer the questions. So thank you very much for the presentation. Thank you very much for the work, and hopefully everyone has a great day.
Thank you very
Thanks,
much.
Joe.
Thank you.